Good evening, everyone. Am I audible?
Yes, sir.
Okay, so we'll wait for a few minutes because some people will join around 7 5. In the meantime, can you see my screen? I had shared the presentation.
Yes.
Yeah, okay, so just this was a small announcement. A few weeks ago, some people were asking whether there will be mock tests for physics or not. So NPTEL has now enabled this service, and you can just simply log on, just go to the NPTEL gate.nptel.ac.in, and on that you'll find a tab called Gate Practice Tests, and there you can register yourselves. This is you're required to register with the Gmail Google ID, and then you can mm, attempt the mock test there. And the mock test will be happening every Sunday from 2 to 5 p.m. So this means at least 5 mock tests you can give, because okay, today is already over, so it's like 8 Jan, 15, 22, 29, and then finally 5th. So you can give a 4 or 5 mock tests. It's a good practice. It's always a good practice to attempt mock tests as diverse as possible. So you may want to avail this opportunity. uh, I'll still wait for more time. In the meantime, if you have any questions or comments regarding uh, regarding special theory of relativity, which we have been talking in the past 5 sessions. By the way, today will be the last session on special theory of relativity. So in case you have doubts or comments regarding the previous session or for today, we can utilize this time until other people join. So I'll mute myself. If you have anything to say, you can unmute yourself and speak.
Sir?
Yeah, go ahead, Mandle.
Sir, actually, I was having a request.
Uh-huh.
Sir, can you please inform this the one who is designing these papers
Okay.
that there are no MSQs included in it.
So it's completely numerical answer type.
No, sir, MCQs are there, but MSQs are not included in it.
Okay, beg your pardon. What are MSQs?
Multiple select.
So more than one option correct. That's what you mean to say?
हाँ हाँ
Okay.
हाँ हाँ हाँ.
ठीक है. I'll pass on this feedback. That's good of you to point out. I'll surely pass this feedback. Thank you.
Good evening, sir.
Harish, yeah, go ahead. Harish, go ahead.
सर आज जो मॉक टेस्ट होना था वो आप टेस्ट नहीं कर पाए थे.
Your voice is not clear. It's to me it's not clear at least. Can you repeat?
सर आज मॉक टेस्ट हुआ था ना उसको आप टेस्ट नहीं कर पाए थे.
I'm not able to hear you clearly. Just type in the chat box. Just type in the chat box. I'm not able to hear you clearly. Harish, type in the chat box.
ओके सर.
Okay, so let's begin today's session. This is Gate Physics Live Sessions Phase 2, hosted by NPTEL. My name is Amit. I'm a PhD student at Indian Institute of Science, Bengaluru. This is week 6. on January 1st, 2023. You are unable to access the test. So Harish, I guess you just, if you have registered it, just I request you to just email NPTEL. So there is a NPTEL email address that they have. Just email on that and saying that you have registered and you're still not able to access the test. They will be able to help you. So since I'm not on the administrative side, since I got to know that this is that they've started the mock test, and some of you had asked in some previous sessions, so that's why I'm just informing you. Okay, if you have mailed, then I guess they'll take care of it, and I'll also just point it out that that some people are having problem accessing the tests. But who was it? Mandlik, you were able to attend the test, yes? Today.
Yes, sir.
Okay,
Yes,
ठीक है.
sir.
Then
Yes, I also did.
other people also, okay, ठीक है. Then Harish, just my request to use, while NPTEL fixes it, my request to you, if you have any alternate Google ID, just try with that. Sometimes it happens that it gets blocked or something, so just try with an alternate email ID, and then okay, then it's a common problem. I'll just, and nevertheless I'll just give the feedback, okay, that many people are not able to access. Okay, so let's begin. I hope you are able to see my screen, yes or no?
Yes, sir.
Okay, January 1st, my name is Amit. This is week 6, session 6, and this will be the last session on special theory of relativity. This we have already talked about. So we are talking about, let me switch on my pen. So we are talking about x, y, z and time, which I denoted like this. And we have special because we're neglecting the role of gravity here, and the two core concepts in this theory we had talked about is that laws of physics will remain invariant. So what do we mean by laws of physics? Like conservation of charge, conservation of momentum and energy. We saw that momentum and energy we saw in the last class itself, that how were they important. In today also we'll go through 3 questions which will further cement this idea. Conservation of charge also. And next, sorry, what are inertial frames? Inertial frames are the frames of reference with zero acceleration. This means either they have to be at rest, this means velocity has to be 0, or some constant velocity. This means it cannot be changing with respect to time. So only then a frame can be said to be inertial. Okay. Next thing is, we talked about the some terms which keep on repeating. So one is observer inertial frame. So this is our inertial frame, which we usually call rest frame. Today we'll also learn this is also known as center of mass frame. We'll see why it's called so, or lab frame. So each of these 3 terms means this frame is at rest, velocity is 0, okay, or earth frame. So there are many names for this frame. So just any one of these you can assume it to be at rest and inertial frame. So there's an observer sitting at the origin, which is in blue frame, we call this O. Similarly, there is another frame which we call S prime. This is also called, by the way, the first frame, blue frame, is also called S frame. S prime frame with the velocity v moving in the positive x direction with respect to the rest frame. And note, this velocity will have to be constant velocity, let's say 5 I cap or whatever. Okay, it has to be let's say 0.5 c I cap, because it has to be close enough to the speed of light. And there are some events. So what are the events? Events can be like some event p happen with coordinate x1, y1, z1, t1, and same event we'll see here as p prime with everything primed, x1 prime, y1 prime, z1 prime and t1 primed. So these are what are called events. Further, this was the core thing, that space-time interval is an entity, mathematical entity, which we define in this way. So delta s square c delta t square, this is called the time interval. Just straightforward because there's a delta t here. So what is t2 minus t1? This is the first event p. Correspondingly, there will be a second event x2, y2, z2 and t2. Correspondingly, there will be a q prime here, x2 prime, y2 prime, z2 prime and then t2 prime. Pardon the overlap here, but that's the idea. And this is called the space interval. Space interval. Together, what they make is what is called as the space-time interval, in this case squared, and this remains invariant. This is the basic of the special theory of relativity, based on which we talk something about transformations. So let's say you are given some coordinate here, p, x1, y1, z1 and t1, and you need to find what is the p prime here. x1 prime, y1 prime, z1 prime, or t1 prime. So you can use the Lorentz transformation, because non-primed entities are known, that means t and x are known, v is also known, inertial frame, this is s prime frame, this is s frame, rest frame. You can use this formula to get it, or and vice versa. If the prime entities are known, this means you know the position and time in S prime frame, then you can get the event in S frame, the rest frame, by using inverse Lorentz transformation, where gamma is depends on the speed of frame, which is usually denoted by this formula. Building on that, because we know that velocity is dx by dt, or for sake of simplification, let's say delta x by delta t. We had derived that, I think the third class, we had derived the formula for 3D, and these are the formula that we have arrived at. So again, if ux is known, so there is a particle here with moving some velocity ux, uy, and uz. So there's some particle p here, right? It's moving like that. Similarly, this particle will also be seen moving to this O prime observer as ux prime, uy prime, and uz prime. So what are those ux, uy, uz? You know everything. We know v, we know ux, uy, z. You can calculate this. Similarly, alternatively, if you were given the prime entities, right, you were given the velocities in this s prime frame, and you were required to find the velocity in s frame, you can use this formula. So you can do that, and the trick is that you can see that this just sign is inverted, so this minus, it's plus here, and that's all. Everything else remains the same, right? Apart from that, we saw some real effects, like not real, I mean, which we not perceive, but these are actual events that we have experimentally demonstrated, right? So we saw that we had length contraction and time dilation, where let's say there's an object here like this is at, let's say, at rest here, and so it's at rest here in this frame. This is, so we introduced two concepts like proper length. So proper length is length in objects frame of reference. Similarly, we saw proper time, which is denoted by t prime here. So the proper length is denoted by l prime here, or sometimes it's also known as l naught. Proper time is time measured in objects frame of reference. So remember these, and we solved a couple of problems. We've also seen the derivation, and so that's all. That's about this. Finally, we come to the main topic for today, that is regarding mass, momentum, and energy. So this is the frame, the rest frame, the S frame. Let's say there is a particle P, which is, if it's not moving, its mass will be m naught, hence it's called rest mass. If this particle starts moving, its mass will change. It's known as relativistic mass, where you know gamma is our good old 1 minus v square over c square, where v is the velocity of this particle, right? Similarly, if you know the mass, we can get the momentum. I should say u is the velocity of this particle, because I'm using u here. So m times u is the relativistic momentum. M is the relativistic mass, you can see here. Similarly, we can get the energies. Rest energy is simply E naught equal to m naught c square. Note the suffix. This denotes rest, and m naught c square. Similarly, relativistic energy will be this, and this will be equal to mc square, right? So it's fairly straightforward. So all the knots have been removed. So E equal to mc square, and this is the formula. This is actually E naught here. This is a suffix. Sorry about this. Similarly, you can find the kinetic energy. Kinetic energy will be total energy. This is total energy here. This is total energy, this one. So total energy minus the rest mass energy will give you the kinetic energy, which is given by E minus E naught. So you can simply subtract these entities, or you can also say mc square minus m naught c square, right, which will come out to be gamma minus 1 m naught c square. So you see these shortcuts sometimes written, but it's fine. You can, if you just remember the basic formula, you will be fine with that. And this entity is known as mass energy equivalence, the famous Einstein's expression, right? So some people who have joined a bit late, so this is an announcement that from this week onwards, NPTEL has started the mock test for physics also. If you are interested, and I strongly suggest that you should, you go to the website gate.nptel.ac.in, go to practice tests and mock tests, and just register with your Google ID. And this mock test will be conducted for every Sunday 2 to 5 p.m. So this means at least 4 Sundays or 4 to 5 Sundays remain. I strongly encourage you to take this opportunity. Right, coming back to the problem, we had started to solve this problem in the last class, so I'll just go ahead with again. So there is a particle of rest mass m. So what I'll do, I'll change the problem statement. So let's make it m naught, rest mass m naught, so that it's easier to apply the formula. It's moving along the positive x direction. So this is a mass m naught. It is moving in positive x direction. It decays. So at some time it's moving, but it decays in two photons, gamma 1 and gamma 2, as shown in figure. The energy of gamma 1 is given as 1 GeV, and this is given 0.82 GeV. G is giga electron volts. Sorry, G is giga, EV is electron volts. We need to find the value of m naught. Note, I have changed m to m naught everywhere, and this is a numerical answer type question, and once you find the answer, we need to round off to 2 decimal places. I again emphasize this is important to round it off properly. Right, as always, before we begin, we find out what are the inertial frames. So as always, usually in this problem there is only one frame. So let's say let's consider the S frame. In this rest frame or lab frame, we see a particle of which is moving let's say at velocity u. Okay, this is a particle. This particle is moving at a velocity u in positive x direction. So, and there's only one frame required here, which is S. So is it inertial? Yes, it's inertial because it's at rest. So S is inertial. S is inertial. Moving frame, there's no moving frame in this direction, so this is not applicable. Number of dimensions, okay, so number of dimensions here are actually 2. You see, because these photons that are moving, they will have the momentum in this. I should first draw the coordinate system. Sorry, this is x and this is y. So you can see these photons, they are in a 2D picture. So here we have 2 dimensions. So this picture is 2D, x and y. So what I'll try to do is that, first of all, what we'll try to this is m naught, this is 1 GeV, or let's just call it E1. We'll put the values later, and let's call the energy for this is E2. Right, so we saw that and this is all happening in the lab frame S, where this particle is moving with the velocity u. This is the velocity u that you can see here. So so everything is clear here. So first we'll apply the conservation of momentum here. So conservation of momentum would mean that first what we'll talk is before collision we'll write, so, or before decay in this case. So before decay, the total momentum will be this. So we can write P initial. P initial would be total mass m, relativistic mass m, which is denoted with capital M using this formula, times u. Okay, and m can be written as gamma times m naught times u, where gamma would be equal to 1 minus this will be u square over c square. Okay, so let's now talk about what will be the final state. So we'll write P final would be equal to, okay, so I should also mention in direction, this will be in I cap because it's moving in positive x direction. So this u is entirely in I cap. So gamma m naught u I cap. So P final, we can see that it will have 2 components, x component, y component. So let's write as P final x I cap, this is the magnitude, plus P final y j cap. So I mean, it's fairly obvious that since the initial momentum is only in x direction, this term would be 0, right? So what I'll try to do is, first I'll try to evaluate only the momentum along the x direction. Okay, and we know that for a photon, I'll write this here, for photon, momentum P equal to energy by C. So what will this give us? This will give P1, the momentum for photon 1 will be E1 upon C, and P2, the momentum for second photon will be again E2 over C. Note that these are the magnitudes. Okay, these are the magnitudes. So now I know that this has some momentum P1 and this has some momentum P2. Now let's try to resolve these momentums. So this is P1, and so along the x direction it would be P1 cos 45. This will also be P1 sine 45. Just a second. All right, similarly for the second photon, this is something like this. So this will be P2 cos 60, and this will be P2 sine 60. Okay, so now I try to evaluate this P final x. So it will be P1 cos 45. This means P1 by root 2 plus this component. This will be P2 cos 60 is half, so this will be like this. This will be I cap plus, let's do this component, this will be P1 by this component P1 sin 45, which will be again P1 by root 2 plus this quantity. Note that direction is minus y, so our coordinate system was like this, x and y. So this will be minus, not plus, minus P2 sin 60 is I believe sin 60 is root 3 by 2. Yeah, okay. So now what I'll do, I'll just plug in the values. So I'll use my calculator. If someone knows the values, they can tell me, otherwise I'll have to use. So P1 by root 2 will come out to be, P1 was what was P1? P1 was 1, sorry, E1 was 1, so it will be 1 over C root 2 plus P2 was 0.82, so 0.82 over C into 2. Okay, this will be P1 over root 2 will I cap, sorry, plus P1 over root 2 will again be C root 2 minus this will be 0.82 into root 3 by 2C. Okay, so I'll just so this will be, the first term will be 0.7, this will come out to be 1.12 over C I cap. Actually the units here are GeV is also there, so please remember that this is, we are all talking in GeV because this was 1 GeV plus, so this will be 1 by root 2 would be 0.707 minus 0.82 0.8 root 3 into 0.82 divided by 2, this is coming out to be 0.71 J cap, which makes sense. This gets cancelled out. So we know the initial momentum was in x direction, and here also we confirm that the initial momentum, there is no momentum in final y direction. So from this now we do P initial equal to P final, we get gamma m naught u is equal to it's this entity 1.12 GeV over C. This is our first expression. We obtain this expression due to the conservation of momentum. Second, very straightforward, we will just go to the conservation of energy. So again the initial energy is E initial will be equal to m, so note the rest mass was m naught, so m c square. The final energy would be, it's very simple, it will be E1 plus E2, which will be equal to 1 plus 0.2, so 1.82 GeV, right? I'll write this expression, the first expression here. So gamma m naught u we obtained was 1.12 over C GeV. This was expression 1. Expression 2 would be mc square equal to 1.82 GeV. Okay, so what I can do is, okay, so I can evaluate the value of capital M from here, which is, note that capital M was, this is nothing but capital M, the relativistic mass. I can also write as mu equal to 1.12 by C GeV. So I can calculate the value of M here, which will be 1.82 over C square GeV, and put this in this expression. So this will be 1.82 over C square into u, note u was the velocity of this particle, over 1.12 over C GeV. So GeV gets cancelled, this gets cancelled, 1C gets cancelled, so this will come out to be 1.12 over 1.82 C. So 1.12 over 1.82 is coming out to be 0.615 C. Now we have obtained u. So what I'll do is that now if I know u, I can put in this formula, right? I can put into this formula, or I'll use this actually. So this can be written as gamma. So first I'll evaluate gamma. So we know that gamma was equal to 1 minus u square over C square. So I'll simply put this 1 minus 0.615 C square over C square. So this gets cancelled. So this squared, so this is coming out to be 1.27. Gamma's value is coming out to be 1.269 actually. So what I'll do is that I'll put this value here in this expression, in expression 2. Okay, so I'll write that gamma m naught, m is nothing but gamma m naught C squared equal to 1.82 GeV. Okay, So gamma I know is 1.269. This will give me m naught equal to 1.82 over 1.269 GeV over c square. So 1.82 divided by 1.269 is coming out to be 1.435. This is coming out to be 1.435 GeV over c square. This is the rest mass. In the question we were required to find the rest mass m naught. So we found out the rest mass m naught is 1.435, note the units, GeV over c square, up to 2 decimal places, so I'll round it off to 1.44. so that's our answer, and so it's very straightforward problem, and we solved it like this. I'll again reiterate what we were required to do is that this particle was moving with some velocity u in x direction. This is our coordinate system x and y, and we first applied the conservation of momentum, and we saw that only the y components of these two photons cancel each other out, only the x component remains. And secondly, what we saw was that we applied conservation of energy. Note there are two variables here, that's why we need two equations. The first variable was m naught, second variable was u, and gamma is a function of u. So remember that. So if you know u, you know gamma. So two variables are there, m naught and u. Hence we need two expressions. First is conservation of momentum, second is conservation of energy. So that's all. I'll pause here. If you have any doubts or comments, please go ahead. All right. If there are no comments, then I'll move on to the next question. Yeah. So this is the second problem on how the particle physics. In the first or second class I talked about that how special theory of relativity is used in particle physics. So this is again a problem of that. So you see this thing, center of mass frame. So what's happening is that when there are more than two particles, we can find the center of mass of a system of particles. So that's what it's talking about here. And if there is no external force, center of mass will always be at rest, right? If there is no external force, it's inertial, not at rest, it will be inertial, because you can see that m, and the second law is force equal to ma, right? If there is no external, this f is actually f external. This m is total mass of the system, a is the acceleration of the system. So if f external is 0, then a will come out to be 0, which means system is inertial. So when we're talking about center of mass frame, if it's an isolated system, it will be at rest. So hence we can also call it the rest frame or the lab frame, which we had talked about. So it says that two protons each having energy. So in some rest frame, we see two protons, these are approaching each other, they collide. Okay, so they have some energy, 7000 GeV, and they collide. So this is before, and afterwards they produce some protons and antiprotons. So they produce some protons, let's say some p protons, and some antiprotons, which are denoted by p bar. So we need to find the number of antiprotons, the maximum number of antiprotons. So that's the problem. And as always, are the frames inertial? There's only one frame, first of all, the center of mass frame, which is inertial because there's no external force we are talking about. So yes, it is inertial. So center of mass frame, inertial. So that is correct. Moving frame, there's no other frame, all the frames are S frames, so this is not applicable in this case. Number of dimensions, we're only the question is silent, but this problem can be solved only by taking one direction problem, because it's saying they're approaching each other. So we can say one dimension, and that dimension will choose it to be x, and this is the positive x direction. Right, before we go ahead, I need to talk a bit about the particle physics. So the subatomic particles like protons and neutrons are made up of something called quarks, right? So there are 6 types of quark: up, down, charm, strange, top and bottom, these are their symbols. And these are the anti-quarks, means they're opposite to them in the sense that they have the same mass. So the mass of them will be the same, but their charge, and there is some other entity called baryon number, strangeness, every other thing will be different. Only the mass will be the same, every other thing will be just the inverse of it. So for instance, if it's up quark denoted by u, its charge is plus 2/3, and its baryon number is 1/3, its strangeness is 0. For u bar, which is the anti-quark, the charge will become minus 2 by 3, the baryon number will become minus 1 by 3 from 1 by 3, and strangeness will become from minus 0 to plus 0, which means it remains 0. Similarly, you can see for other things. The good thing is that when we talk about proton is made up of 2 up quarks and 1 down quark. So you see up, this one, then one more this, and then one this. So up, up, down. So if we calculate the total charge, it will be 2 by 3 plus 2 by 3 plus 1 by 3. So this will have 2 by 3, this will have 2 by 3, this will have 1 by 3. Total charge will become 2 by 3 plus 2 by 3 plus 1 by 3, right? Sorry, minus 1 by 3, my bad. So it will be 4 by 3 minus 1 by 3. So total charge will become out to be 1. Let's calculate the protons baryon number. So up, up, down. So it will be 1 by 3. So baryon number will come out to be 1 by 3 plus 1 by 3 plus 1 by 3, because up, up and down all have baryon number as 1 by 3. L. So there's another entity called lepton numbers. There are 3 lepton numbers. We'll see in the next slide. Le, L mu and L tau. This is electron lepton number, muon and tauon. Both for baryons they are 0. So these are baryons. Proton is a type of baryon because the baryon number is non-zero. Strangeness we can see is 0 because 0 plus 0 plus 0 will be 0. Similarly, what is antiproton? As I talked about, it's just the inverse. It's the antiparticle. So the mass will remain the same. Note, mass for both of them is m0. However, charge will become inverted. It will become minus 1. Similarly, the baryon number will come from plus 1 to minus 1 because you see u bar has charge minus 2 by 3, then minus 2 by 3, and then plus 1 by 3. So they will come out to be minus 1. Similarly, baryon number is minus 1 by 3, minus 1 by 3, and minus 1 by 3. So baryon number will come out to minus 1. The lepton number will not change, and strangeness is also 0 for up and down charm. So this will remain 0. So this is an important thing that you need to remember, right? And this is the complete table. So in the first 6 rows, you see what are called leptons. These are called leptons. These are called mesons, and these are 2 examples of baryons. And there are symbols are given. So lepton number will be used. You can see for mesons and baryons. Just look below this line. Lepton number will, all the 3 lepton numbers Le, L mu and L tau are 0. Right? For electron, neutrino, lepton Le is 1. The other lepton numbers are 0. And similarly for leptons, baryon number is 0. You can see that. Right? And you can also see the strangeness in this table. The thing is that you will have to memorize this because usually these things are not given in the problem. Sometimes they may be given, sometimes they may not be, but you will have to memorize them, at least for these very popular entities like proton, neutron, pion, and electron, muon and tau. Right? Now, interesting thing is that there are conservation laws. So first conservation law is that in any transformation, strangeness number must remain conserved. That's the first law. The second law is that for any transformation, baryon number must remain conserved. That's second law. Third law says L tau will remain conserved. Fourth says L mu will remain conserved. And fifth is in any transformation, Le must remain conserved. Overall, the summary is that all these 5 numbers must be independently conserved. Means B must be conserved, L tau, L mu, strangeness, Le, everything has to be conserved. Only then that transformation is allowed. Right? So now we'll come back to our question. So this is the problem that we're given, that before collision, this is the system. There's a proton. You can see on your left. These are 2 protons approaching each other with speed u towards each other. And these are their entities. We saw that Q was 1, B is 1, L is 0, 0, 0. This means Le is 0, L mu is 0, L tau is 0, strangeness is also 0. What happens that we were given that after they collide, some p numbers of protons are produced and some n numbers of antiprotons are produced. So protons are in blue, antiprotons are in red. You see this is the symbol of antiproton, p bar. You see that every entity has been just like inverted. So q plus 1 become minus 1. Right? So now we'll apply 1 by 1 conservation laws. First conservation law is charge must remain conserved. So let's see what is the charge on the left side. So on the charge on the left side is 1 plus 1. Charge here is 1. Charge here will be 1 times p plus minus 1 times n. So I can write as minus 1 times n. So this will give me, so I'll just rewrite it here. So it was 1 plus 1 equal to 1 times p plus minus 1 times n. This gave me p minus n equal to 2. First expression. Now we saw the 5 conservation laws. So S must remain conserved. So S is 0 plus 0 on left side. On right side is 0 times p plus 0 times n. So this gives 0 equal to 0, which is good. B must remain constant, the baryon number. So baryon number here would be 1 plus 1. Here the baryon number will be 1 times p because there are p number of protons. So 1 times p plus baryon number is minus 1 here. So minus 1 times n. So this will again give us p minus n equal to 2. So this must be satisfied if this transformation has to be successful. Finally, we saw that all the L's, that is L, Le, L mu, L tau, have to be conserved, which you can clearly see is all of them are 0 here. So 0 plus 0 will be equal to 0 times p plus 0 times n, which means 0 equal to 0. So all the lepton numbers are conserved, strangeness is conserved. However, if the charge and baryon number has to be conserved, this has to be followed, that p minus n must be equal to 2. This is important. So what we, from the last slide, we get that p minus n must be equal to 2. This is our first expression. Now we'll apply conservation of momentum, right? So we know that the energy of both of these protons, in the question it was given, it was the same. So initial momentum, you can clearly see if the mass is, the rest mass is the same and the energy is the same. So you see that gamma m c square, gamma m naught c square, sorry, is total energy E. So both of them, they have the same energy and they have the same mass. This means gamma must be the same. This implies gamma is same for these protons. This implies U must be the same, hence U is that. So this implies P initial would be gamma m naught U I cap plus gamma m naught U minus I cap. Their momentum will cancel out each other and hence the momentum would be 0. So initial momentum we can clearly see would be 0. Let's talk about the final momentum. So I'll write 0 equal to final momentum. So final momentum would be, so there are, okay, this will be a bit tricky. So there are p number of protons, each have the velocity vp1, vp2. So I can write the total momentum would be gamma m naught vpi, right? Where sigma running from I runs from, this will be gamma I, actually gamma pi, it runs from 0 to p. Similarly, I'll write this I equal to 0 to n gamma ni m naught vni. This is the complete expression. Very tricky. We'll leave it at that because we don't know the individual gammas. We need to evaluate what is the individual velocities, then only we will get to know gamma. But you can clearly see the number of variables here are p plus n, because there are p velocities and again n velocities. So there are p plus n variables. And we only have one expression and two expression, that's it. When you go to conservation of energy, the total energy will be that was given in the problem. So total energy will be 2E, which was given in the problem. So 2E. Again, the energy here will be a bit problematic. So again, we'll have to write like this: gamma m naught c square, gamma pi m naught c square. I runs from 0 to p plus I runs from 0 to n, gamma ni m naught c squared. Again, there are p plus n variables here, and this is only the third expression. So we have three expressions and p plus n variables. We cannot solve this. Simply we cannot solve this because it will have infinitely many solutions. However, there is a key thing that we missed. Remember, the question talked about that what will be the maximum number of antiprotons. Maximum number of antiprotons. Right. So we need to maximize n. Now, so what happens, you know that any energy has two components. This is the kinetic energy, so I can say that kinetic energy will be equal to E minus E naught. So let's say if you want, so all the energy that is there initially can either go on creating these masses or it can go in their kinetic energy. So if you want to maximize that more number of particles should be produced, what we should do is we'll assume that they are at rest. What I mean to say is that how to maximize n or p. It's a very simple thing. You assume all the particles are at rest. This means nothing goes in this kinetic energy. So all the momentum is 0. This means we can produce more and more number of these particles. Okay. So that's the key here. We'll assume kinetic energy final to be 0, momentum to be 0, and kinetic energy would be 0. Right. So then what this expression becomes, this expression will now get simplified to, because now if it is red, gamma will be 1, right? So what we'll get is m naught c squared will be common, p plus n. This is what we'll get. P plus n m naught c square equal to 2 times E. This is the expression that we'll get. So what I'll go is, I'll go to the next slide. We got P minus n equal to 2 and m naught c squared P plus n equal to twice the initial energy, which was 7000, right? So now we can clearly see that, and we know the mass of proton mass is 1 GeV. So I'll put it here as 1. So this gets cancelled. So GeV over c square. So this is 1 over c square. This gets cancelled. So what I'll get is, yeah, correct. So I get P minus n equal to 2 and P plus n equal to 14,000. Now two variables and two expressions. So you can simplify it. If I P plus n equal to 14,000, P minus n equal to 2. So if I just subtract them from each other, it will get 2n equal to, this will come out to be 13,998. This implies n will come out to be 6,999. So n is coming out to be 6,999. Why we could do the simplification for energy? Because note this, the maximum number of antiprotons, right? The maximum number of antiprotons will be produced when all the initial energy, which is this, into 2. So if all 1400 giga electron volts, it can either go into mass or it can go into kinetic energy. If we have to increase the number of antiprotons, this means we have to increase the rest mass. Then if we reduce, if we minimize this kinetic energy, then we can have maximum of rest mass energy. So this is the rest mass energy plus kinetic energy. That's what we did. And obviously before we just saw some particle physics. So I'll pause a bit here because this might be a bit heavy. And if you want me to repeat anything, whether it's quarks or it's momentum or energy, please, I'll just pause a bit and I'll let you take it from here. Was it too much?
हेलो
Yeah, Harish.
सर, इसमें मैक्सिमम नंबर ऑफ एंटी प्रोटॉन पूछ रखा है, ठीक है?
Yes.
तो इसमें मतलब जैसे भी कोई भी न्यूक्लियर पार्टिकल है, ठीक है, तो उसका मतलब दो जो कंपोनेंट बनेंगे कोलाइड के बाद, तो उसमें और भी पार्टिकल के बारे में पूछ सकते हैं, मतलब क्वेश्चन में.
Yes. So what Harish is asking is that in this question, this question was asking us to determine the number of antiprotons. So what he's saying is that usually what we had talked about till now, we needed to talk about the energy and mass of the energy or momentum of the final particle, right? But here they are actually talking about the number of particles. So yes, anything can be asked, but if you pay close attention, the formula that I have used have not changed. The formula still remain only the three. The relativistic mass is gamma times m naught. The relativistic momentum is m times u, which is again gamma times m naught times u, and the energy is total energy. Kinetic energy is total energy minus your rest mass energy. So that thing remain the same. The basic concepts remain the same. The ingredients can be played around with. Yeah. So just you just need to have be sure about what they are talking about. That's it.
Okay, sir.
Okay. All
Sir,
right.
that problem from nuclear physics.
Sorry.
This problem was from nuclear physics.
Yes. So the thing is that so the people I view is at a problem of both actually. So you cannot solve this problem if you don't know relativistic kinematics, and even if you know relativistic kinematics, you cannot solve this unless you know what is an antiproton. So you must know the charge of antiproton, because remember in this problem we arrived at this first section, P minus equal to 2. We arrived that because we must know the charge of antiproton, that's -1. So if you don't know this very basic thing about particle physics or nuclear physics, we cannot solve this problem. So this problem requires knowledge of nuclear or particle physics as well as relativistic kinematics. So this is one of those rare problems which requires in-depth understanding of two topics. So that's why I kept it. That's why I kept this as a part of relativistic kinematics, because this is the most complex problem that you can have in this field. Right, shall we go ahead? I have one more problem of not so difficult, relatively simple. Again, just a reminder, if other people have joined, please go ahead and avail these mock tests. Right, again, problem for particle physics which requires knowledge of relativistic kinematics from 2014. So we are given this process where, note that again, plus and minus, they denote their antiparticle. So if you consider this to be the particle, this would be antiparticle. Similarly, if this is the particle, this is the antiparticle. I already talked about the antiparticle has same mass, but all the other attributes like quark composition, lepton number, they all just flipped. So they change their signs. That's what I mean to say. So this is the process that is given to us. The minimum kinetic energy of muons in the center of mass frame produced to pions pairs at rest. Okay, so we need to find the kinetic energy of muon such that kinetic energy of pions is 0. See, pair at rest, and we are talking about in center of mass frame. So I already talked about center of mass frame. So you can see, we'll see in the next slide, the center of mass frame, everything is happening in this frame. We also call it the rest frame. Right, as always, we'll just talk about inertial frames. So center of mass frame, there's no external force, so this means center of mass frame is inertial. Center of mass frame is inertial. Secondly, is there any moving frame? No, so it's not applicable in this problem. Number of dimensions, the question is silent on number of dimensions, but we can simply assume it to be one dimensional problem, which we take it to be x-axis. This is the positive x-axis. Right, again, these are the things that we saw earlier, the quark and anti-quark. So the symbols are like this. I wanted to introduce pion here. So its rest mass is m pi, which you can see here. So the pion is composed of an up quark and d prime quark, d bar quark, which means it's composed of this and this. So let's try to calculate its charge first. So its charge would be, so u charge is plus 2 by 3, and d prime, the charge is plus 1 by 3. Charge will come out to be 1. So I have written here charge equal to 1. Now next, the baryon number B. So again, we see the baryon number of u is 1 by 3. So this will be 1 by 3. And the baryon number of d bar is minus 1 by 3. So this will be plus this. Hence, B prime will come out to be 0, which is written here. And since this is a meson, so all of them have lepton numbers equal to 0, which we'll see in the next slide. Strangeness, you can see for this as well as this, strangeness is 0 plus 0. So 0 plus 0, this will come out to be 0, which we can see here. Now the second part of the question talked about is muon. So this is a muon. I should go to the next slide for muon itself. So I told you these are the what we call the leptons, the first 6. The first 6 are leptons. So these are leptons. These are mesons. And as we saw, these are the baryons. Okay, let's just look at this fellow here, muon here. So muon has lepton number Le equal to 0, which makes sense. But L mu is 1, right? And L tau is 0, which again makes sense. It's not a baryon, so baryon number has to be 0. And it's also not strange, hence strangeness number equal to 0. And you can also see for the similar entities for pion. So pion is not a lepton, so all the 3 L numbers will be 0. Its baryon number, it's not a baryon, so baryon number has to be 0. And it's not strange, so the strangeness number also will be 0. As we saw that for each of these entities, each of these 5 entities have to be conserved, right? Independently, that's important. Independently, they have to be conserved. This means in a transformation, strangeness, B, L tau, L mu, Le, will evaluate each of them separately. So this is before collision. So we have 2 muons, mu plus and mu minus. So you see the rest mass is the same. However, since this is the antiparticle, so you see the charge, this is the antiparticle mu plus. So this charge has changed from -1 to +1. Baron number will not change. However, the lepton number, which is plus 1 here, so this is L mu. The middle one is L mu. It's say plus 1 to minus 1. Strangeness is 0, we saw in the last slide. And this is the after collision. So after collision, these are at rest. Hence, the velocity has been set to be 0. And the mass remains the same. And we see that the pion, for a pion, we see that the charge here is minus 1 and here the charge is plus 1. So what I'll do is, first, the 0th law is charge must remain conserved. So I'll write the charge here. So charge is 1 plus minus 1 is equal to plus 1 charge of it plus minus 1. So it'll come out to be 0 equal to 0. So this is satisfied. Second thing is S must remain conserved. So it will be 0 plus 0. You can see 0 plus 0 should be equal to 0 plus 0, which, so this is also correct. Third is B must remain conserved. So it's B equal to 0 plus 0. It's again 0 plus 0. So this also remains conserved. Third thing, Li must remain conserved. Now here we have to be a bit careful. So first what I'll do, I'll evaluate Le. So Le is 0 plus 0. 0 plus 0 is equal to 0 plus 0. So Le is satisfied. Let's talk about L mu. L mu is minus 1 plus 1 equal to 0 plus 0. 0 plus 0. So this will come out to be 0 equal to 0. This is also satisfied. Finally, L tau. L tau is 0 plus 0. You see the third entity here, L tau. This is equal to again 0 plus 0. So this implies 0 equal to 0. So Li is also satisfied. So we see Q is satisfied, S is satisfied, B is satisfied, Li is satisfied. Okay, this question did not require us to do that. But there are some problems which are asked in which they ask you whether this transformation is possible or not. These are the steps you must follow. Check for Q, check for S, check for B, check for all three LIs. Okay, Le, L mu, L tau. If you do this, the question will be correct. Excuse me. Yarish?
सर मतलब हमें चेक करना पड़ेगा, मतलब इस टाइप का कोई भी क्वेश्चन आता है कि ये मतलब से ये रिएक्शन संभव है या नहीं है.
करेक्ट.
राइट. तो सर यदि कई बार क्वेश्चन भी आता है यदि ये संभव नहीं है तो मतलब कई रिएक्शन क्या है कि वीकली इंटरेक्शन ईएमटी मतलब इलेक्ट्रोमैग्नेटिक से मतलब संभव है, स्ट्रॉन्ग इंटरेक्शन से संभव है.
That is okay. So what he's asking is that, so there are two types of questions. Harish is saying there are two types of questions. First is, the first thing itself is whether it's feasible or not. Second question is, if it's feasible, what is the pathway, right? So that depends. So feasible or not, this is the feasibility check. So conservation laws have to be followed. This first thing. Second is, by which pathway is it possible? So that depends on the particles here. You see, just let me go back. So you see this table. So the interaction between these particles is not strong. The interaction between these particles is not strong. So it's a bit different here. I'm forgetting about that basic whether, but I'm sure leptons the interaction is not strong. So if you ask about strong or weak interaction, so it's not strong here. So first you have to check the feasibility, and then whether it's strong or not, then you have to check that. But right now I'm not aware that where are the strong interactions, where are the weak interactions. So I'm not equipped on that. So I just read the basic of this for the limited purpose of this problem. So we saw that all these four remain conserved. As always, first thing we'll try to conserve the momentum. So we'll write the initial momentum on the left side. So initial momentum would be gamma mu times u1 minus, note this is moving in the negative x direction, minus, so I'll write it as gamma mu1 actually, gamma mu2 mu u2 should be equal to 0 plus 0. Why? Because these are at rest. The question says they have to produce at rest. Alright, so what I'll get is gamma mu1 into u1 should be equal to gamma mu2 into u2. Mu is there on both sides, it gets cancelled. So this is the first expression that we get. Note where gamma, the gamma expression is 1 minus u square over c square. So for gamma 1 it will be u1 square over c square, and gamma 2 will be u2 square over c square. That's the first expression. Now we come to second expression. Second expression, conservation of energy. So I'll write the energy for this. So I'll write E mu1 plus E mu 2. Energy is a scalar quantity. This should be equal to E pi 1 plus E pi 2, or I should say mu plus mu minus. I'll write it again. E mu plus E mu minus should be equal to E pi plus E pi minus, right? So let's first try to evaluate E pi plus. So E pi plus will be nothing but the rest mass energy because it is at rest. So it will be m pi into c square. For pi minus is also at rest, it will again be m pi times c square. Note, they both have the rest mass is m pi. Similarly for this, right? Yeah, so similarly for this, what we can get is this will be gamma 1 m mu c square plus gamma 2 m mu c square. So okay, I should go back actually. So when we saw this, so let's put the value of gamma here. Okay, so it will be u1 over 1 minus u1 square over c square. This will be u2. So if you try to go ahead and solve this expression, you will evaluate that magnitude of these are magnitudes. So u1 will come out to be equal to u2. Why will that be? Because you can simply see the right side is 0. So the left side, the one of the simplest solution is when the magnitude are equal, then the gamma will also be equal and their momentum will simply cancel each other out. So if you try to solve this, you can simply see if I put u1 equal to u2, LHS and RHS match means u1 equal to u2 is a solution. I'll go ahead with u1 equal to u2. So u1 equal to u2, let's call it u. Okay. So I come here, so this implies that gamma 1 will also be equal to gamma 2, and let's call it gamma because u1 is equal to u2 equal to u. So I'm u1 equal to u and u2 equal to u. So this will become 2 gamma m mu c square equal to 2 m pi c square. C square gets cancelled. So 2 gamma will come gamma will come out to be m pi. Write this here, gamma will come out to be m pi over m mu. So this will come out to be 140 over 105. This is 35, 4 by 3. So gamma is coming out to be 4 by 3. If gamma is 4 by 3, we know it's 1 over 1 minus u square over c square, which is equal to 4 by 3. So you can just, it will be 9 by 16, 1 minus u square over c square. So u square over c square will come out to be, making some mistake somewhere.
So 1 over 1 minus u square by c square.
Yeah, so I put it that side. This is correct, I think. Is it not? Hold on a second. Write it here. Gamma we obtained as 4 by 3. So this is 1 minus u square over c square, right? Actually, we do not even need to bother about the value. So we need to find the minimum kinetic energy, right? So we need the kinetic energy, we know is total energy minus E naught. So total energy we have obtained is this 2 m pi c square minus the rest mass energy that we have obtained is again very simple, is rest mass energy of muons. Okay, so rest mass energy of muons will be 2 times m mu c square, right? Correct. So this will come out to be, yeah, correct. So this will come out to be, so 2 times m pi minus mu is 35 c square. So it's coming out to be 70. So this is MEV, right? So this is MEV over c square into c square. So it's cancelled. I feel I'm missing something. I don't know why. Can somebody help? This some term I'm feeling like that I'm missing something as if. Okay, let's go ahead. Let's try with the different. Gamma equal to 4 by 3 I obtained. So total energy will then be equal to, gamma times m mu times c square into 2, because there are 2 muons. So this will be equal to mu is 105, 4 by 3 into 105 into over c square into c square into 2. So that will come out to be 3, say this is 35, so that's 140 MeV. Yeah, so total energy is 140 MeV, and the final rest energy is yeah, correct. I'm fine. So 35 into 4, it's 280 actually. Yeah, so this is 280. 35 into 4 so total energy initially is 280 MeV, right? And final energy is and initial rest energy is 2 mu c square, which is this 210 MeV, because 105 into 2, hence the rest energy is 70 MeV. So the minimum kinetic energy required is 70. So that will be the answer. Sorry for the confusion in the last. Let me just confirm the answer first. Yeah, so total energy I have obtained to be 70 MeV. Note that this kinetic energy is the total energy, because remember this 2 here. So the minimum kinetic energy of muons in center of mass frame. So in the center of mass frame, so we need to calculate the value of we need to go into center of mass. So in that, the velocity will become half. So energy will become half, because in center of mass frame. So this will come out to be 35 actually, not 70. I'll just prove this. Why I'm saying this is, Harish, just 1 second. Let me fix this. Because there's a bit of a confusion. So I'll do it over here again. So gamma was coming out to be 4 by 3, right? So I'll write it 1 minus u square over c square is equal to 4 by 3. So I take it on that side, it will be 1 minus u square over c square. Okay, right? So this will be 9 by 16 equal to 1 minus u square over c square. So u square over c square, if I bring it this side, it will be 1 minus 9 by 16. Right. So this is the speed of one of the muons, remember that. And so kinetic energy of a muon will simply come out, or I could have simply done that. So kinetic energy of a muon would be equal to total energy of muon minus E naught of a muon. So total energy will be nothing but gamma mu times c square minus mu c square. Yeah, this is correct. Now I recall. So gamma is 4 by 3 mu c square minus mu c square. So mu c square I can take common. So this will come out to be 4 by 3 minus 1. It will come out to be 1 by 3. Mu was given 105 MeV over c square into c square. C square gets cancelled. It gets cancelled. So what I'll get is 35 MeV. So that is the answer. That is the kinetic energy of the muon. That is what we were required to find. The minimum energy of muons is 35 MeV. Each muon is 35 MeV. So yeah, that's that. Harish, go ahead.
सर ये यहाँ से 70 मेगा इलेक्ट्रॉन वोल्ट कैसे आए सर?
So Harish is asking, how did I get 70? So this is okay. So I should clarify. You see this factor of 2, right? You're seeing this factor of 2, right? Because there are 2 muons. So hence this factor of 2 comes, and hence it's 70 MeV, right? But we are required to find in center of mass frame. If we were in rest frame, so that's what I'm talking about. If we were in rest frame, this means, so what's happening is that, so this muon is traveling in this direction and it has some velocity u. This muon is traveling in this direction, it also has some velocity u, right? So what happens is that the momentum actually gets cancelled, but their energy.
1 minute sir, sorry sir. Sir, ये kinetic energy आपने किसकी निकाली, पायोन की या म्यून की?
Which kinetic energy you're talking about?
70 mega electron volt.
This is kinetic energy of muons. This is kinetic energy of this system. Kinetic energy before collision. This means of this system. Before collision.
सर बिफोर कोलिजन, तब हम इसमें टोटल एनर्जी में ये मास है वो इसका क्यों ले रहे हैं सर, पायोन का?
No. Okay, so you're saying why we are taking this 2 m pi c square? That's the question.
Yes.
So because
Yes.
we obtained that the total energy, initial energy must be equal to total final energy, correct?
Yes.
So total initial energy, so what I'm saying is this total energy which is there, right? This should be equal to the final, whatever the final energy is. Final energy is nothing but 2 m pi c squared, right? Or if you don't want to take this, okay, if you don't want, that's what I did here. So I'll do it again. So kinetic energy would be equal to total energy of muons minus E naught of muons. Okay, total energy of muons is nothing but total energy of pions, because total energy must remain conserved, right? Total energy of pions is 2 m pi times c squared, and rest mass energy of muons is 2 mu c squared. So if you do this, you will get 2 into 35 into c square and sorry mev over c square into c square, you will get 70 mev. This is kinetic energy of this system, muon system. Okay, so I could replace it because their total energy will remain the same, will remain conserved. That's why I could do this. It's not possible every time, but in this case it was possible. So that's what we did, and this is for the muon system. For individual, if I need to find, and since the velocity will be the same because final momentum has to be 0, we saw that u1 equal to u2 equal to u. So if that has to be satisfied, this means kinetic energy will be split 50-50. So I can see kinetic energy of mu plus will be equal to kinetic energy of mu minus will be equal to 70 by 2 equal to 35 MeV. So that's what we are doing here. Okay, is it clear that how did this term come out to be m pi c square? Because the total energies are the same. So I'll summarize this in this problem again. We first saw a basic of particle physics, like what is a pion, which we saw somewhere over here. Yeah, so what is a pion we saw, and then we evaluated, and then we made sure that all these 5 numbers remain conserved, the charge and the strangeness, baryon number, and all the 3 Lapton numbers. Finally we applied conservation of momentum, and we learned that while applying conservation of momentum that u1 has to be equal to u2, which is equal to u. And then finally when we applied conservation of energy, and using this expression we solved it, and we noted that the total energy of the system is coming out to be 70 MeV. Initial kinetic energy of the system is coming to be 70 MeV, which has to be split in the 2 muons. So we did that, and it come out to be 35 MeV. So that's how we do it. So that's it from my side, and I'm completed with the special theory of relativity. From the next class we'll be doing electronics.
स्लाइड और दिखा
Sorry,
सर, एक स्लाइड इससे पीछे वाली.
this one,
Next.
this one.
Next.
You want me to go back?
Sir,
or
go forward. Go forward.
This is last slide.
सर यहाँ पे काइनेटिक एनर्जी आपने बियॉन्ड सिस्टम की ले रखी है. टोटल एनर्जी बियॉन्ड सिस्टम इक्वल टू टोटल एनर्जी पाइयन सिस्टम. That will equal, right?
Yes, that will be equal. That's the conservation of energy law. Correct.
ओके सर, यदि काइनेटिक एनर्जी मान लीजिए हमें इनिशियल काइनेटिक एनर्जी दे रखी हो और फाइनल काइनेटिक एनर्जी निकाल दी हो, तब हम मतलब लास्ट वाला जो ई नॉट म्यून सिस्टम का ले रखा है वो पाइयन सिस्टम का ले लेंगे, राइट?
नहीं, see, the only thing is that you have to equate the fact remains very simple. E final has to be equal to E initial. So E final I can write as total energy, actually total energy final. So I can total energy final I can write as 2 m pi c square plus kinetic energy of pion system equal to 2 mu c square plus kinetic energy of muon system. Okay, This is the expression. Now whatever is, so this is given, this is given. Here these two, here this was 0, so we could use this expression and you can solve the problem whatever you are talking about. So if this is given, then you can calculate this. If this is given, then you can calculate this, provided the rest mass are also given in the problem. So this is the expression. The total energy has to remain constant. Whatever the unknowns are and whatever the knowns are, you have to just put into this formula. That's it. There's no fancy thing happening. It's very straightforward formula.
Yes, sir, clear.
Okay.
I am confusing here.
Okay.
Okay, thank you, sir.
Okay. So that's it. That's it from me for this class. I'll hang around for a few more minutes if you have. Okay, just before you leave, for the next class, we'll be starting electronics for 3 sessions. So I know I've done electronics. If you find time, if you're interested, you can go through the videos from the previous few months where I talked about the electronics. And I have also uploaded the schedule for what I'm going to discuss in the next class. So next class will be digital electronics. So we'll talk about DAC, ADC, and I'm forgetting the other 2 things, Boolean algebra, yeah, and logic gates. So I have discussed them, but I'll discuss them again because I find some new questions from gate itself. So we'll discuss them, and yeah, feel free to join.